Right. Good morning, everyone. I hope you can hear me. Can you confirm?
Yes, sir.
Right. Thank you. And then let's start. Now, in today's one, what we are going to do, we are going to talk about another software development technology. And then, so last time also we discussed some methodology, but this is particularly focused on how we can develop a more secure software system. So this is known as development before the fact technology, and which focuses on developing a safe, error-free software system. So let's start then. Now, if you look back when this particular development methodology came in, the main person behind this was a lady. She was American computer scientist and system engineer called Margaret, and she works on two places, but mainly DARPA Labs and MIT, because at that time her task was the lead the software development for sending people to the sky, especially for Apollo and Skylab mission. So you know that they are very safety critical issues because you are sending people, and these spaceships operated with the software that you develop, and you make sure that you don't have any mistakes. You know what will happen, right? So if you are, of course, you can't make any mistakes. So there, the team and then the Margaret realized that there's a very important that when you're making software systems, that you should not make any mistakes, because these are very critical systems which involve with people lives, right? So the main issue in software development is the errors. So this particularly development before the fact technology is the starting point was the study of software errors. So how you should minimize these software errors. So let's see the details of this technology, try to understand what motivation behind, right, for the development of this technology. Now, this was a very unique approach, and it was a visual model. I will share you like some of basic representation of the systems. So the main task of this technology is we are using visually creating the models, right? Now, when you say visually creating a model, right, we want to make sure that you will create a bug-free code together with the documentation. So the task is you will have a bug-free code and the documentation, and then you are going to automatically, generate that. So they came up with what they call 001 tool set, and that tool set they have developed through their unique approach. Now, if you look back the software errors, the main error, especially when you talk about the errors in software, so they may cause with the what we call interface errors. So that's what mainly one of the major causes of software issues, right? So when we say interface errors, no, it's things like now, for example, when you exchange data, for example, between systems, we will have different data types, right? Now, for example, one problem is, let's say you are sending a string from one system and the other system is expecting an integer, right? Then there are some issues, right? And sometimes when you call functions or methods, and if you put up incorrect parameters, or if you use in wrong context, so this will be a problem, right? And things like version incompatibility, things like the different components, if they use different versions, the libraries, the API, then there could be, errors, right? And real time, now remember this spacecraft and all, they will have real time operations. So if you have like things like timing issues, right? Uh, usually you will have some time frame, the response time, and then if we are not, meeting it, then there'll be an issue, right? And problems, things in user interfaces. So, for example, you have misalignments in the elements, incorrect data displays, and so on. So these are the ones we call interface errors. So these interface errors are the major cause usually in when you have a very complex software systems. So the focus is addressing these or reducing these interface errors. So by doing so, we can expect to have very improved, reliable, safety software development. Now, as you can see, there are like key principles in any technique of designing, software. For example, we were discussing in the very beginning about software development life cycles like waterfall, and then agile like Scrum. So they have their own set of principles. Like in Scrum, for example, you have iterations, you have sprints, you have backlogs, and so on. So the key principles for this methodology is we are focusing on error prevention, not correction. Now, usually what will happen in software development, we create software, and when there's a problem, we go back to the code, we review, and then we try to fix it, right? But this is different. Now, in development before the fact technology or the development methodology, they design system focusing error prevention. That means you are going to reduce future errors, right? Think ahead of before you are getting an error. So then the procedure will be is very systematic, rigorous, the software development. So there will be a lot of benefits of using this in different applications and the domain, especially when we have safety critical systems where you cannot make any mistakes, right? Although we develop software, So majority of the time, it might affects the people lives as well. Now, let's see like what are the issues with traditional system engineering approach, which sometimes we traditionally use, right? Um, Now, the first thing, as I told you earlier, is uh, our traditional systems, we always have, you know, you develop the code and then you have a bug fixing, right? You identify the bugs and they fix them. So basically, the focus is the fixing the problem and not the prevention, as we have discussed. Now, the problem with the fixing means now to fix the code, sometimes you have to have the team allocated. So you have to spend hours of identifying error and fixing it, which means it will reduce the quality of the product. And also you are going to waste the resources. Now, anyone who's trying to find the bug and, spending time on removing the bugs is a wasted resources, because if you can prevent while you are designing, you can save a lot, right? The problem mostly in traditional software development is there will be a mismatch of when you capture the requirements. Remember, in early stage of the software development, we will capture the requirements. So then the problem is there will be difficulties when you want to integrate, when you have objects, the modules, and the phrases. So this is the difficulty in traditional software system, right? And then ambiguous and incorrect definitions, incompatible interfaces, and error propagation. I told you about interface issues earlier, and that may lead errors, and error will be propagated through the system, right? So if you make an error at some point, it will propagate within the system. And then if you look at very traditional software development like waterfall, we have lack of adaptability to changing user requirements and the environment. And this will lead to the issues in the maintenance. We know that once we develop and deploy, we have to maintain the software. So the maintenance cost will be high, right? So the costly maintenance and risky development will be there in our traditional systems. Now, the technology that we are going to discuss is known as a preventive approach to software development. So, and this methodology will address many problems we find in traditional systems. And it promotes error prevention, and also it promotes efficient development. So in the first place, it'll prevent the errors, and then it may lead to efficient development. So this is one alternative for traditional methods. Actually, recent ones along in this way. So you can find things like design by contract, a similar methodology. Again, that can address the interface errors, right? So there are many. So, but so this is one such, algorithm, software development technology. So now let's look into details. So from the start, that means when you're defining things in the beginning, so what you do is you have to define things correctly. right? Things like, remember I talk about these data type issues. So things like them, you are very careful in the very beginning. So you have to fully understand the system requirement in the first phase. And then not only that, you have to understand how different components, because there will be several components communicating each other. And then you need to understand what are the components and how they interact before you really code them. Now, for example, nowadays, what we do is we don't fully understand the system. So, for example, even at the agile, what might happen is you might, select set of features and you try to implement, and then you try to iteratively develop. The problem with that is then you don't, fully understand the whole system. So that is good, but for a safety critical system like sending people to mass, for example, so you cannot do like that, right? So which means you make mistakes and then you learn, it's very costly mistake, right? So that's the point. So you have to define everything from the beginning. So early focus, this is we known as early focus in this, and it helps to identify the the problematic area, the interface errors that might occur in different components, right? Then so when it comes to this, it will model both the application as well as its the life cycle as well. So that means you create detailed models, and especially when you have like some parts of the system or subsystems, so you will also identify how this subsystem will interact, right? So using this technique, you can understand how the system behave, and then you can identify, you can rectify any issues before the implementation. So that's the main import. So inherently, you integrate all the objects and then their functions, right? Okay, more information. Now, the advantages of these technologies, they can maximize the reliability of the software as well as the flexibility. And it also support runtime performance analysis and design integrity, enhance potential for reuse, automation and evolution, and built-in quality and productivity. Now, remember, so we talk about the importance of identifying the requirements and the interaction of the system models, as well as system modeling. Because as we have discussed, it's always focused on prevention, right? The point is you don't make any mistakes. And then you have to have very comprehensive documentation. So that should be there. And then you can iterative refinement, right? Okay, so let's look at the different approaches of this, what we call now, we understand or understood how the development before the fact technology, handles. So when you look at the two techniques, one is you create and you identify the bugs and correct them. The other one is the prevention. So the curative is you should eliminate errors through continuous testing. So that's what we normally do in our traditional software development. But preventive, that means in this particular case, we should prevent errors from occurring. Similarly, in curative approach, we accelerate development by adding resources. Now, you see, when you develop software system, if you want to improve the software development time, maybe you add resources, which will cost a lot of money. But in preventative, technique, what they do, basically they improve the efficiency through the reuse, as well as they try to eliminate any unnecessary processes. Sometimes we have not focused this, right? Because without looking at overall whole software system, you might not you understand this, how you may reuse them or eliminate any unnecessary processes. So let's discuss what you mean by effective reuse, because this is very, very important. And that's the technique that we promote within this technology. So the reusing error-free component, which improves the efficiency as well. So that means we guarantee that, okay, if you're using that particular component, so it will not create any errors. So this reusing, it starts with the beginning of the life cycle, not at the end. So from the start of this, so you look for reusing the components that you have developed now, things like your functions, the modules, and so on. So with emphasis on reuse, you can save a lot of time and money, because you don't need, have unnecessary developments, right? So point that we want to make is, if you are using every 10 successful reuses, it can save 10 unnecessary developments. So that's the point that we will highlight under this. Right. Now let's look at into details. The technology we have used is called formal theory. Now, formal theory, I don't think you have done it, but the basic idea of for formal theory is, basically you use reasoning. This actually normally comes from the mathematics, or even in our theoretical computer science, we use this formal theory. Now, if you remember that we have, our previous school head received ACM award for development of operating system. So they have used formal theory to prove that it's secure, the system. That means mathematically they have proved that the system is secure. So similarly, this can be used. Basically, what it has is, it use some languages, symbols, the rules. So where you can use that to understand or analyze very complex problems. So simply, here also, they will use the formal theory, right? So with that, they are capable of define and integrate any aspect of any system. So you can have system-oriented objects instead of object-oriented. So usually we focus on the object interactions in object-oriented analysis, for example. But instead of looking at each individual object level, you can look at, system level, which we call as system-oriented objects. So for example, when you use this, then we normally call it semantics dependent, which means we focus on the meanings, but it's not based on it's syntax independent, right? Which means you don't really worry about the syntax. So since we use this, we can say it's a formal and friendly language we will use. Now, to build this system, when you want to right? So we have to define the model with the language, and we can analyze it for the corrections. And then you can generate production ready software implementation and documentation. Then you test it, refine the system, and then every steps you have inherently testing. So this is the main points when you want to build a system using this development before the fact technology. So the foundation for this is you have to use axioms and universal set of objects, and you have to apply throughout the entire life cycle of the development of this. And the users will be managers, engineers, and the end users. So you will have the things coming from the systems theory, formal methods, formal linguistics, and object technologies. So this will lead actually, so the first time then they developed this for the Apollo space missions, and they have identified that it reduced the interface errors. So that means the issues with the different components of the software system. So it started as we have already stated. So this is a bit old, but it's still we can get things out of this in 1968. And we will, they have actually focused on the developing software for man-rated mission, because which means you are sending mans to interface. So the errors usually they had in their already existing software systems, about 75% of the errors were the interface errors. And that's what they want to minimize. So they categorize errors, and they derive a theory to how to eliminate these interface errors. And that's how they came up with the development before the fact software development strategy. Right. So let's focus on integrated modeling environments. So in here, you have a very recursive and reusable approach. Remember, we used the term reuse earlier, and it will be recursive as well. So we are not going to use very detailed method. As I told you, is it use a lot of mathematical concepts, but we are going to at least going to look at two things here. The models that we define, they use something called functional maps. In short, we say F maps. And the other one is we call type maps or T maps. So these two represent two different things. Now, if you start with the F maps, that means function maps. They represent the dynamic world of action, and it capture the functional and timing behavior. And on the other hand, if you look at type maps, represent the static world of objects, and they capture the space behavior. So we can inherently integrate these two things, that means F maps and the T maps. Right. Now, F maps, we call functions, and each node control their children functions. So you can see we are creating a hierarchy of functions. So F maps, we define that each function will control their children functions. Whereas T-maps, we have types, and then each type will control their children type, right? And these types you have in T-maps, you have very primitive operations. And F-maps control transformation of the objects from one state to another. So primitive types usually you will see at the bottom of T-maps. Right. Now I think let's try to understand graphically what these means of F-maps as well as T-maps, right? So we will have two types of nodes you will see here. One is you have functions, the other one is types. So in F-maps, obviously we have functions. So we have functions, and then these are some control structures you will see. So what you can see here is this function is here, and all these are the children functions of this. So this can control all these general functions. Similarly, if you take this, right, then this has another two children functions, right? So this is how we place. Right. Then what we have, the next is we can have what we call the T-maps. And in T-maps, what we have is that a type map, right? You have type and its method. So remember, we were discussing the function issues and also the type issues. So then you can see the hierarchy, and then you can also look at some child types as well. So that's the first part. Now, how do you design with these F-maps and T-maps? So they start looking at their T-maps of your application, the types of the application. And then you have F-maps. They also partition functionality based on the T-map structure, because you start with the types and the in the first place. So T-map will give you a structural criteria to evaluate the functional partitioning. And then F-map and T-map divide the system into functional and natural components. So you see, we discussed earlier that the errors came up from communication issues with different components. So now this time, using these two techniques, functional maps and the type maps, we can systematically, separate the components. So what will happen, since you have some basis for this, then it will inherently integrated, and it's understandable from the very beginning, because you use graphical representation from the whole system. And then you will also notice how the hierarchy is built. So if your functions will also have children functions where you can control from the top. Okay, so let's next focus on the primitive structures in integrated model development. Now, when you look at primitive structures, they are dependent, independent, and then you can have decision-making relationships, right? And then you can have what we call formal set of rules for each of these structures. So by doing so, what we can do is you can eliminate the interface errors. So you can look at some examples. So F-maps and the T-maps in the system designing. So this is actually very toy example we are going to look at just to understand how we will use it, but the actual use will be a bit complex. So we are going to look at very toy problem, which we call make a table example, right? And notice you use in this, you can notice the traceability of the objects. Okay, so remember we have uh, the idea of this example of make a table is how do you build a system to make a table. So initially I told you, you have to identify all the requirements. So we have to define clear objectives and the requirements in the beginning. So you can say the requirement is let's build a system for making a table, right? And we know the requirements, the table should have legs, right? And you may use hard or softwood, and you can have a round or rectangle top, which are the let's say the requirements. So you have to capture that first. The next would be like you start with the T maps. Remember, I told you you have to start with the T map, the types, right? So for example, the table, you start with the type, right? So this has two. So the top could be wood, right? And then when you look at the wood, that could be either soft or hard, right? And then table, you have the other part is legs, right? And then you can have leg in wood, right? So likewise, you first focus on the types. Now, once you understand this, right? Or once you develop the type map, then you start creating the F map, the functions. So now to make a table, we will create a function called make a table, and then you provide the parameters. In this particular case, we can have flat wood and then also round wood. Likewise, you can provide the parameters. So then you will see the control structure will have join. In this particular case, we are separating out the function because remember that we have children functions. So this is the top one where you make a table, but we now change the top of this into one. We can say, okay, we'll assemble the top and the legs. So which is one part. And then to create a top and the legs, we have another function we call make parts, which will give you the top of the table as well as legs, right? So now you can see the main functionality here is a maker table. Now we have put into two functions where one will create the top of the table and the legs, and the second one will just assemble the top of the legs from the outcome you get from here, take it as an input here, and then you will get the table. Now let's go inside now here. So now how to put, top and the legs. So that means we need another function to create the top. So we call it make a top, and another function to make legs, right? So which means, so before we come to this, now we have created two functionality to create the top of the table and to create the legs. But when you're creating top of the table, remember we discussed idea earlier that this could be, right, soft or hard, right? So that means we have another two functionality here to create the top. So you can either, it says O, you can create either a soft one or you can create a hard one. So as you can see, this is a very toy example, right? right? Just to give you an overview of how the thinking process comes in. So to summarize, what we have discussed so far is, in this example, in development before the fact technology, the mainly we start with the types we call T maps, graphically represent the relationship of the different types, and then we will create what we call the functional maps. And when you want to implement, then now you can actually make use of these structure, which will have a overall idea of how they fit in together, right? Now, let me give you another example. For example, in this particular case, uh, creating functional maps as well as type maps. So let's say you want to create a user management system in a database. So the functional, the type map would be like, for each user, you have to define the type. And for example, if you have a user, you can have user ID as integer, name as a string, email like a string. So that's something like the type map. And then functional maps could be, let's say, the relationship. So for example, the mapping from user ID to their name and the email could be done in functional maps. So this is the idea usually we will use. Right, let's move on. So when you look at the applications of this, you if you want to apply into very real-time distributed environment, this could be one technique to consider. And then this could be used in banking, manufacturing, and even the software development. And there are many more. So what the other point is, you can use uh, parallelism here, as well as you can trace like what is going on, because you have a very clear picture. The functions when you're creating, you don't just create it now. Right now, when you develop an application, depend on our requirement, we create function. It's not like that. You have seen that we have a hierarchy always, where now everything will be connected, and you have a clear structure. So if you look back, advantages of this is, as we already discussed earlier, this will reduce interface errors. Interface errors means the error between different components of the system, things like type errors, type mismatch, right? So you can actually reduce these errors. And also, it'll improve the definition and organization. So you can see always you have some representation where you can improve the defining of the system. Remember, I told you the importance of requirements, gathering requirements in the first place. And also, since we are creating a hierarchy, you will have improved organization as well. And you can also notice that this will facilitate the reusability and the flexibility within the software development. Okay, the problems. Now, although we discuss throughout this example, the use of this particular technology for the software development, there are, challenges as well as limiters. Now, one thing is understanding this and applying what we call the primitive structure is very challenging, because there will be a lot of mathematical concepts we are using. First, you need to understand that. That is one issue. And then how do you incorporate this into existing system? Now, let's say uh, some software developer technology, you can, change the way you use and you can directly apply. But if you have existing system, there are some issues how you may actually incorporate these ideas of the structures from the very beginning, right? And also, how do you ensure the modeling of complex systems? So these are very, challenging, and the limitations of this technology. Right. Back to primitive control structure, since we discussed. Remember, now here we have, when we define our types as well as define our functionality, we always have parent-child relationships. So the parents, they control children. So there we expect a dependent relationship, right? Or independent relationship, or a decision-making relationship. So you will have each and every set of rules, you have, primitive structures. So you can eliminate the interface errors at the definition type, because remember, type errors, for example, will not happen because you will decide on what types you are using, right? And this will maximize any errors that you might actually generate while you are implemented, because you think ahead and you have a very planned structure which you can use to eliminate any errors happening when you're designing the system. Right. So let's go back to our example, the maker table. So the top node functions, what we have seen there is called flatfoot and roundfoot inputs. And then the table is the output. So you can see, we have seen when you say make a table, you can make parts and then you can assemble. So that's how we start identifying the primitive structure, because the first part is, okay, when you say a table, you need to first make parts, that means the top and the legs, and then you need to assemble. And then you have to have different decision-making functions. So you have seen we use join, we use include, and in some place we have seen O as well, right? So these are like what we call decision-making functions that we have actually considered in our maker table example. Right, then if you look at again types in Tmaps, right? So you can see, we will see each type in Tmap, we decompose into children types with primitive structures. And you have seen, notice in our previous example, the table we can put into top and legs, right? So you can use dependent, independent, and decision structures with objects. So let me go back to the picture again. So we have already seen this. So what we have discussed earlier, let me reiterate. Now here, the first thing that we have discussed is you start from the top where you have the main function, you make a table, where this is, we will decompose into assemble and make parts. And this is a join, which means you create parts and then you assemble. Then the second stage, what we have seen is the make parts, meaning you are making two parts, the top and the legs. And both of these will have include, right? So the making parts include make top as well as make legs. And then if you go further down, when you say make top, so you will have either you have a finished softwood top or you have finished hardwood top. So this is O. So this is how we have structure. Similarly, our T map, you see we have table and then we have top and the legs. And the top is one of hard or one of soft. Whereas legs, right, a set of we have legs in wood. So as you can see, so in our example, we have discussed how we may actually use this toy example, make a table to describe F map and then T map, right? So the properties of once you define systems with these primitive structures like what we have discussed earlier. So what was the primitive structures that we have discussed? So we have decompose into the types with the hierarchy and the functions, and then you will use different join, include, or different functions. By doing so, we can have event interrupt driven system. Traceable and recoverable objects, you see that we have a hierarchy, and then your priorities are defined. So for example, we can see unique priorities within the system. That means when you're defining both types as well as the functions. Then independencies and the dependencies detection for parallel and distributed processing will be easier because you can see the hierarchy within the system. And it's also maximize the flexibility and capitalization on the parallelism. So these are like some of the properties once you define a system with primitive structures. Then we have what we call the defined structures for system design. So under this, what I want to discuss is how to accelerate the process of defining and understanding the system. So non-primitive structures can be created. You can use for asynchronous, synchronous, or interrupt scenarios. So which will lead to use a reusable pattern for both F maps and T maps. Right. So let's look at define. We can have primitive structures, and you can provide flexibility to repeated use as well as ordering and the selection of objects. And then you can have rules for non-primitive that are inherent from rules of the primitives. Then you can also have asynchronous and synchronous behavior and define with the primitive structures and conclude the user-defined structures. So for example, coordinate task system, you can be dependent, communicating, concurrent, synchronous, and asynchronous functions. So these are the how you may actually define them. Right. And then the reusability of these T maps. Now, for example, when we create user-defined type structures in T maps, we have used several of them. We use tuple of, or set of, one of, tree of. These are called type structures when you're defining T maps. So again, once you use this can maximize the potential for the reuse. So remember, we want to promote reusability within this development structure. Right. So let's look at the complete system definition. So we can integrate a set of F maps and the T maps. And then if you look at this for a manufacturing company, so we can have the system ready for automatic development and production ready for. So FMAPs, they can decompose until they reach the primitive operations on TMAP types, right? So decomposing means, remember, we started from the maker table, then table top and the legs, and then you can go to top, for example, you can have a hard top or a soft top and so on, right? So if you look at FMAP, so you have primitive operations of the TMAP types. Then if you look at TMAPs, they can decompose until you get primitive types, right? Basic types that you are going to have. So these will be decomposed in TMAPs. Okay, let's look at another example is full system employee system. We can use object defined by TMAP, manufacturing company. So for example, we can look whether the employees are full-time or part-time, and then you can use locate the using the name. So that means you can use a function to find the employee based on the name. So for example, the primitive operation could be you can check whether that particular employee, whether it's a full-time. So this primitive operation is full-time, which will determine if the employee is a full-time. Right. Now that we got some idea about how to make use of FMAPs and TMAPs in here, so let's look at how to discuss inheriting relations and the behaviors. Each type structures that we have seen, they look for their own possible relations for parent and child types. And then abstract types, you can decompose with same type structure, inherit the same primitive operation as a behavior. Remember, the leaves nodes, you have to have primitive operations. So if you look at the example that we have seen earlier, manufacturing company employee, and their inherent primitive operations from the type is tuple of, right? Could be the one of the primitive operations. Reusing primitive operations. Now, if you look at the child, move to child parent operation from type structure. So for example, you can have a function called move to employees manufacturing company, which can be used to navigate to an employee's object containing manufacturing company object. So the types that can be non-primitive, primitive, or a define another type of subtree. Okay, so more on universal primitive operations. So when you start with the TMAPs, the type maps, it provide you have universal primitive operations for controlling objects and the object status. And then you can create, destroy, copy, reference, move, assess value, detect and recovery errors, assess object type. So this also facilitate and manipulating understanding of different object types. So use of TMAPs and OMAPs help system identify itself better. So I think it should be FMAP, TMAPs and FMAP we have used. I will make the correction. So we can understand the system because we have a graphical representation. Right, TMAP properties and the control. So each the type map property is ensure the proper use of objects in FMAP. So that's why I told you, like, you start with the TMAP and then you go for FMAP. And then you have control spatial relationship between objects. You can reference to an object state cannot be modified if there are future reference to that state. And then reject values existing all types of error recovery. Now, using primitive operations, let's look at another example. Rotate. You have rotate arm hardware system. You can use as primitive operations for numeric calculations. So universal operation, you can use replace twice, and then you can have function qualifies to use unique T-map parent-child combination. Right. To discuss last two slides of today's session, T-map expressive power and the relations. Now, when you use type maps, we have seen that we clearly hierarchy for the types, and then the leaves you have primitive types. So T-map, its expressive power enhanced with explicitly defined relations. Now, if you look at a stack of bearing, you can describe using a set of structure type. And then you can use retainer hole with ball object independently related to cap surfing. So this is another way that you can independently define the relations. Right. To finish our discussion, remember this technology, we started looking at the development technology, the first place, like a fold, like agile. But in this one, they actually this particular technology or development methodology came around 1960s, which is quite old, but the concepts was very clear that you have graphical representations, you model the whole system clearly, which we will emphasize on reuse as well as proper documentation within the development. So you can see the term reuse is the powerful feature of development before the fact technology. So everything you develop can be reused and can be used for integration. So F maps and T maps, the define, and then we can use each other as reusable. So that's the main thing that we want to highlight. So further reading of this, I suggest that you read the course book. So this is, there are some more examples, which is the chapter 11 from the book, which I will post the chapter 11 to get the brief idea. Now, one thing that I want you to, make use of is the thinking behind this, thinking behind the technology, which define or hold the system using the type maps and then the functional maps that we have discussed. Right, that's all what I have for you today with this. Our next part would be, we are going to actually revisit what we have discussed in the beginning. That means the topics that we have discussed in your previous one, where we focus on the system development. So we will look at more examples here. So we will discuss how software development technologies could be used, as well as graphical representation, which help you to define this. So with that said, so we'll conclude for the session. But before that, let's mark the attendance. So let me share the attend on for you to mark the attendance. You can see, please mark the attendance.